Hi, welcome to another lecture of JS Yatra, and in this particular video we are going to learn about breadth first search, that is BFS. The level of this question is medium. So without wasting any time, let's get started. As an example, which is node A containing B and C, B containing D and E, C containing F and G, and we want to perform BFS on this particular graph with the source as A. Let us have a look at the visual representation of the same graph. You can see that there is a parent node or the root node A containing B and C as the vertices or the nodes. So nodes are also called vertices, and B is containing D, E, and C is containing F and G. Now if I want to apply BFS on this particular graph, the output would be something like ABC, DEFG. And how is that happening? Is really very simple, that the BFS graph starts traversing from the root node, and it starts traversing the the neighbors. So B and C are the immediate neighbors for A, so it traverses B and C. Now when it comes to B, it starts traversing the nodes that are present on the same level. So we have C over here, but C is already traversed, so we will not pick this up. Instead we come to D and E, and simultaneously when we come to C, we come to F and G. So how is that thing working out for us is very simple, that when the node A finishes traversing, it comes to B, it comes to C, and it traverses B and C, and it pushes D, E, F and G. These are the nodes connected via the edges. So these vertical lines are the edges, which you can see over here. So D, E, F and G are kind of pushed on a queue, and when we are finished traversing with B, then comes C, and then comes D, E, F and G. So the data structure queue plays a heavy role in this particular traversal method, because queue is a data structure where first in first out principle is applied. So when I want to traverse this particular graph, I want to traverse A, so A is coming first, so A is being rendered first in the as output. Then comes B and C, so B and C are again pushed on the queue data structure. And so let me create the queue for you as well. You can see that. So okay, imagine this is a queue over here. So when I start traversing the node A first, so I push A onto the queue, and I start traversing. The first item I get from the queue is A, so I output A. I this is the output array, so I push A in the output, and B and C are the connecting nodes via the edges, so I am pushing B and C onto the queue. Okay, now I have already dequeued from the queue, so A is gone, and I come to B now. When I start traversing for B, I encounter D and E, so I push D and E. I push D and E onto the queue. It is not pushing. The technical word for pushing an item into the queue is enqueue. So I enqueued D and E on the queue, and since I am currently reading B, so B is being put on the output array like this, and this is being dequeued. Now I dequeue C, so C is being dequeued. This is gone. Now when I am reading for C, I encountered F and G, so I'll push F and G over here, and now I have already dequeued C. Now I'll dequeue D, and this would come over here. Since D is not having any connecting nodes via the edges, similarly goes for E, similarly goes for F, similarly goes for G, and this is how you generate a BFS. So this was the walkthrough of the BFS that we are going to implement, and you have already noticed that I traversed each and every node or the vertices of the graph. So V are for the vertices, and I am also traversing each edge. So when I am at A, I am traversing edge for B. When I am on B, I am traversing for D, I am traversing for E, then for C I am traversing for F and G. So I am also traversing each vertices, plus I am also traversing each edge E. So V plus E should be the ideal time complexity for each for this particular algorithm that we are going to write. And the space complexity, since we are maintaining a queue data structure, so at any maximum amount of time, since this data structure is not fixed, it is in a continuous motion of nq and dq. So at any particular time, the maximum amount of nodes at any particular level will give us the space complexity. So at this point, I can see that there are 4 nodes in this particular level. So, and I encountered a case where there were 4 elements present on the queue as well. So ideally, big O of n should be the space complexity, where n represents the maximum number of nodes at any particular given the level. Okay, this is the level 0, level 1, level 2, and so on. So any particular level, the maximum number of nodes that are present gives us the space complexity, because at any time that would be the maximum amount of element present in the array of the queues. So we'll be needing a queue data structure. If you're not familiar, what is a queue? We'll be discussing this in depth in one of the videos. But queue is a data structure where you have an array of elements, and if you push something, that is called an in queue. And if you take out something, if you pop out something, that is a dequeue. So this is a data structure where first in first out principle is followed. It is quite opposite of stack data structure, which we discussed before. So if you push anything onto the queue and you try to dequeue that, then the first element that got enqueued is dequeued first. Okay, this is the basic rule that a queue follows, and we are also going to use the same. We are not going to create a whole queue data structure from the scratch, but instead we'll be using arrays to simulate the behavior of queues. Okay, that is perfectly acceptable. No doubt in that. So let us jump back to the code that we were going to write. So this is the graph which I just demonstrated on the board, and this is the data format which you are going to expect the graphs in. So A is containing B and C, B is containing D and E, C is containing F and G, and D, E, F, G are all leaf nodes, so they are empty arrays. So we'll be using the simple recursive approach, and we'll see how we can utilize the queue data structures in this. The first thing first that we have to analyze over here is that if the graph is empty, then we have to return empty array. So we are checking that if object dot keys of graph dot length equals to 0. Let me clear some space for you so that we can understand it better. Okay, if it is 0, then what you have to do is I'll just have to return an empty array saying that okay, we don't have anything to traverse, so just return empty array. But if we have something to traverse, so I'll first of all const create a queue. This is an array, and we'll keep a track of all the visited nodes because there might be a chance that we encounter a node twice, and we don't want to add that item again onto the queue. So to fix that, we'll be needing const visited as a set. This is a new set which is going to store all the traversed element that we have picked so far, and visited would be something that would give us the final BFS as well. So you remember we had a data structure where we were putting in all the visited nodes. So this is the visited array or the output array. So we need a start point. So we'll add the source. The source is the A, the root node. So we'll add the root node into the queue first. So it would be queue dot push source. and we'll add this visited in the visited set as well. So we'll add source as visited because we visited this source node just now. And I'll create a function const traverse. This is a function, and I'm going to do a return traverse. So this would be our recursive function that we are going to call again and again. So the first thing I am checking that when I am calling the traverse function is the queue empty, because this is a base condition. Once the queue gets empty at this point, then that we have finished traversing the whole BFS graph. So I'll just say if queue dot length equals to 0, okay, then return the visited set, but we have to convert that set into an array. So I'll just do array dot from visited. Okay, so this would create an array from the set. So this is the base condition we have just written, and now is the time to perform the logic. The logic is to uh, like dequeue an item from the queue, add the corresponding like connected nodes in the inside the queue. So we'll in queue. So first we'll dequeue, then we'll in queue the items, and while dequeuing, we'll see that if the node is visited or not. So we'll see that how that works. First of all, const node. This is where we are doing the dequeue. Okay, so this would be queue dot shift. If you're not familiar with shift, we have been using shift for a long time in this particular course. Shift removes the first item from the array, and it shrinks the array to that to that particular length. So let me take you mdn shift. So shift method removes the first element from the array and returns the removed element. So if I just call first element array1 dot shift it and I console dot wrong array1, it removes 1, it gives me 1, and the array is like 2 and 3. Okay, so this is the shift. This is exactly what we want. That is exactly how I wanted to perform simulate a like dequeue. In dequeue, what we do is we remove the first item of the queue. So to remove the first item of the queue, I am using queue dot shift, and when I received the removed item, all I have to do is I have to latch on the extracted node. Let's suppose I extracted B, and then I am going to for example, we extracted A, then B and C are the neighbors. Okay, so these are the neighbors, and we are going to iterate over B and C, and we are going to in queue them in the queue. Okay, so I will do like graph of node dot for each neighbor. For each neighbor, we are going to do something. So what we are going to do is really very simple, that if we have not visited it, so if not visited dot has neighbor. Okay, this is a part where we have already traversed the source. Now we are traversing the neighbors. Okay, so if we have not visited this particular neighbor, then it is a time to visit this, and I just do a visited dot add neighbor. Okay, we have visited this neighbor, and then what we have to do is we are going to uh, enqueue this item into the queue. So this would be queue dot push neighbor. Okay, this was all. This was all I have demonstrated in this example as well. Like when we are taking any item, we are adding into the list, and then we are having this here as well. So coming back to this part, we obviously, once we have finished doing for each, I have to return recursively call this traverse here as well, const traverse, and boom, here you can see that this gave me the BFS traversal A, B, C, D, E, F, G in the BFS fashion. The time complexity is a big O of V plus E. We have discussed how that came over here, and space complexity is big O of n, where n is the maximum number of items in any level that is present. So this was the BFS traversal for you in JavaScript. I hope you understood this topic, and if you have any doubts, then feel free to ask me in the community channel or on the Discord. And this was all in this particular video. See you in the next one. Till then, take care. Goodbye.